Now, Professor, I'm sure you enjoyed that wonderful trailer, but I think you're going to be more interested in the actual presentation. So our design was a carry-on luggage. And this all started with a problem statement, and the problem really was to select the optimal material and treatment processes for a carry-on luggage using MPIs and many other engineering calculations and considerations. Now, this led to a certain set of design requirements. These design requirements are initiated by a set of functional requirements. By definition, a carry-on suitcase is a device used to store personal items within a geometrically constrained enclosure. In doing so, it must be able to withstand the rigors of transportation and not plastically deform. In this case, the deflection could be ignored, as in this instance, the deflection would not be significant prior to plastic deformation. Now, this alludes into the geometric requirements for this carry-on suitcase. Most common airline carriers have a set of geometric dimensions that are 55 by 40 by 23 centimeters, and this is pretty much generic across the board. And in terms of transportation for buses, there usually isn't any geometric requirements. Now moving on to the engineering requirements. The frame must be able to support a load of 10 kilograms in all possible orientations. It should also be able to support these loads with a safety factor of at least 5. It should have a decently high impact toughness so that it can withstand a drop of at least 1.5 meters while being fully loaded with materials and not be dented. It should also be corrosion resistant to relevant corrosion mechanisms when exposed to things such as water, air, and other materials it will encounter on its journeys on the airplane and other transportation modes. Also, some common airlines put a limit of 10 kilograms for any carry-on luggage. The frame must weigh less than 2.5 kilograms, so the individual will have sufficient weight restrictions to be able to fill it up as much as they can. This means that the whole suitcase must weigh less than 4 kilograms, including all other materials such as wheels. This is necessary so that the passenger has sufficient weight allotted to their belongings. This leads into structural design, and I'm going to be entering in my colleague to continue this presentation.
Yeah, so it was determined that the optimal design for our suitcase was going to be a shell frame. So there's many reasons that a shell frame is advantageous to other designs, such as a wireframe. The main advantage is that sheet metal can be used and bent into the exact shape that's necessary, making the manufacturing process easy and efficient. Also, due to its very nature, a shell frame is protected against impacts and drops from every possible direction, whereas a wireframe design might have weak spots. This leads into the material selection process. So we considered 2 possible failure scenarios to determine which one we should use for the MPI. In the first scenario, the suitcase is held upright by the handle. In this case, the sides of the suitcase are under tension due to the load of the containing materials. In scenario 2, the suitcase is laid on its side and supported only by its edges. In this case, the flat sheet of material on the bottom supports the frame of the entire load. On screen now, you can see the calculations for the first failure scenario. We derived an equation where the mass is proportional to the density divided by the yield strength. For the failure scenario 2, a similar calculation was carried out, and we determined that the mass is proportional to the density divided by the square root of the yield strength. We took a common form of aluminum 6061T6, and inputted it into both of the failure scenarios. From this, you can see that for failure scenario 2, the mass is nearly 3 times as high. So failure scenario 2 is much more prevalent and much more likely to cause the suitcase to fail. This is why we use failure scenario 2 to determine the MPI, which is the equation shown below. And failure scenario 1 was ignored for the rest of this analysis. There are many other potential issues that could arise other than just failing under load. One common form of failure is corrosion. So the material must be resistant to many types of corrosion when exposed to materials such as air, water, salt water, various fabrics, and steel. Also, the material should not break when dropped from a height of at least 1.5 meters and have sufficient impact toughness to be able to withstand that. The material must also be age hardenable because this is part of our design process and it's required so the material will be strong enough. And in order for a material to be H-hardenable, it must have several properties. This includes being able to be quenched, a decreasing solubility limit with decreasing temperature. The second phase must be coherent, which means that it strains the crystal lattice and hinders dislocation motion. Also, the material must be very durable and resist exposure to water, UV radiation, air, drops and bumps, and must also have a low flammability for safety reasons. This leads to the final material selection. First, the MPI limit was used to restrict the possible materials, along with all the other restrictions on corrosion, impact toughness, and durability. After this was done, many possible materials were still available. We did further research to determine that an aluminum alloy with a magnesium percentage of less than 2% would be ideal because it would be lightweight, malleable, and offer great corrosion resistance. When price was taken into consideration, aluminum 6061 T6 was determined to be the best because of its cheap price of only $2.71 per kilogram compared to other materials. It is also easy to manufacture, readily available for purchase since it's one of the most common types of aluminum. Moreover, this alloy satisfies all the other criteria listed above. It's H-hardenable, has enough impact toughness, and the required composition. Therefore, aluminum 6061 T6 is the perfect material for this application. Now that we know the material, we were able to calculate the mass of our frame. Given a thickness of 1 millimeter and the surface area from the dimensions above, we were able to calculate a mass of 2.39 kilograms. This also satisfies our constraint of having a mass of less than 2.5 kilograms. Now I'll bring in Sapir to talk about the finishing processes.
Finishing processes is a key element of having a material that's suitable for its application. The first part of our finishing processes is corrugation. Corrugation offers improved durability because there's less surface area in contact with its surrounding environment. Additionally, it decreases the possibility of a shear stress being applied perpendicular to the corrugation lines, causing any form of failure. Moreover, this could be done by rolling it into shape with a groove-type axial wheel that would create indentations into the material, leading it to be corrugated. The next step is anodization. As Amar previously stated, making sure that we have a material that's resistant to corrosion is very important for something that needs to be used on a daily basis. The process of anodization is used to convert the metal surface into a more decorative, durable, and corrosion-resistant surface. This is done by immersing the aluminum into an acid electrolyte bath and then passing an electric current through the medium. A cathode is placed in the anodizing tank, and this causes aluminum to act as the anode. And once the electric current is passed through the tank, the oxygen ions that were released from the electrolyte combine with the aluminum atoms on the surface to create an oxide layer. This is resistant to corrosion. This protective layer is non-conductive and will be sufficient to protect against all relevant types of corrosion, such as reactions with water and air. Additionally, anodization processes allow for different colors on the aluminum, making more colors of carry-on luggage possible for production. A key element in determining whether something could be anodized is the PBR value. This is commonly known as the Pedsworth-Blebing ratio. The PBR for aluminum stands at 1.28. This is between 1 and 2, and means that this could form a protective layer with pores in it and will not cause any forms of corrosion. The next step of the finishing process is stamping and pressing it into shape. This is more of how you get a sheet of metal to essentially become the suitcase. This is done by using a high-end press and stamping machines and using a CNC router to create crevices into a net shape and then create the luggage half. This then leeways into the production schedule. This is a summary of all our findings that will lead to how will this luggage and suitcase be actually made with specific values, and requires no further analysis to have this suitcase be made if it was done in a production setting. To start off, the material needs to be solutionized. How is this done? The 6061 T6 aluminum requires the following processes. The aluminum is heated to 540 degrees Celsius and mixed with the following alloying elements. I'm not going to read them out for you, they're on screen currently. This takes approximately 1.5 hours. This data was taken from the materials atlas cited in the citations at the end of our report and available in the appendices for further analysis. Moreover, the age hardening of this element is its key to its success in terms of strength. The material is quenched, freezing the precipitates in place and not giving enough time for diffusion to occur. This was thoroughly discussed in the ME230 lectures in class. This creates a metastable material, which is non-equilibrium. The material is then aged by heating it below the solvus temperature at 280 degrees Celsius for 100 seconds. This temperature was once again determined from the materials atlas provided by you when we contacted you and asking for references, and this temperature was shown to be the aforementioned one, and the graph that was used to determine such is on the right. It was linearly interpolated and once again mentioned in the appendices. After the material is age hardened, the proper dimensions need to be set in after the sheet of metal is there. Now, this is done by hot rolling the material to a thickness whereby the material could be cold rolled. And we need the cold rolling to have a certain percent elongation, that's 12%. And to do so, you need a certain percent cold worked. This should be done such that the strength is 280 megapascals once it's completed and has a thickness of 1 millimeter. Additionally, it's important to note that as the sheet cools, this needs to be determined experimentally because when something's hot worked, the exact dimensions are not determined due to thermal contraction. Once a material is rolled, it's important to cut it into transportable sheets. By empirical calculations and semi-truck dimensions, once again could be found in the appendices, it has been found that an 18-foot by 6-foot sheet is optimal for having high transportation usage and easy logistics. Once it's transported, the material would come into the luggage making factory. It is then corrugated by the above mentioned picture, and this corrugation was found to be optimized at 0.5 inches radially, and every 1.5 inches have a 0.5 inch radial corrugation. And this is quite often seen in the luggage industry due to its combination of aesthetic pleasure and being close enough such that there's added values of strength along the corrugated direction. Once this is done, the product needs to be stamped into the net. Using precision cutting equipment such as a CNC punch press to create a net which the unbent outline of one side of the luggage could be seen. A potential net is shown in the image to the right. After this step, a worker or an automated machine could press the material into shape using an industrial press, then it is then shaped into the exact design of the carry-on luggage. After this is done, an anodization process could take place in order to prevent corrosion and add a decorative, colorful layer. The steps for this are as follows. You soak the material clean for 5 to 15 minutes at 130 to 180 degrees Fahrenheit. This is then rinsed. Then it is etched in sulfuric acid for 5 to 12 minutes at 130 to 180 degrees Fahrenheit. Then it is rinsed once more. It is then deoxidized for 5 minutes at 70 to 75 degrees Fahrenheit to dissolve the gray and black alloying elements on the surface. Once again, it's rinsed. Then it's anodized with an 18-volt DC current for 30 minutes. Once again, it's rinsed. Then it's neutralized using sulfuric acid via a sodium bicarbonate dip. Once again, it's rinsed. Then a dye is used, often an organic one, with the aid of AC current to be able to include the dyes in the pores of the anodized aluminum oxide layer to give a decorative finish. Again, it's rinsed. Then it's sealed by steaming it with DI water to close the pores, holding the dye in place. And finally, it's rinsed. Once all this is done, you have a piece of aluminum that's both in shape, protected by anodization, and the color that we want. And once this could be done, workers in the factory could put everything into place and put components such as the wheels, the edge covers, the handle, and the interior lining.